Come back for this one. This is one a day 30, and this is example one for that that it has four parts. And so we're going to go through each of the four parts for this particular integrand. This is for a solid region bounded by the plane 12x plus 20y plus 15z is equal to 60. In the first octant, we want to assume that the density varies as a position of time given by uh, rho of x, y, and z, which is equal to 1 plus x plus y plus z. And we want to evaluate the moment inertia about the x-axis, which is this integral that you see here with the rho that is corresponding to this rho here. Okay, and so in part A, we want to do the order of integration in the order of dz, dy, and dx. And the hint is to consider the projection onto the xy plane. Okay, going through the components of the notes and how to attack the different orderings that you have here. And so since the last two variables are x and y, it's going to be the projection of on the xy plane. And so if we look at the projection of the plane into onto the surface onto the xy plane, looking for the words here, you're going to get that it's a line with this solid region. It kind of forms this triangle here. And so you can see that the x value that corresponds to the y-intercept in the first quadrant is going to be at 5, 0, and then the y-intercept is going to be at 0, 3. And so this is the value of dx here. This is the rectangle that would form that. So the first thing we need to do then is, given this information, is kind of determine what is the equation of this line. And so if we solve for y here, we get that y is equal to 3 minus 3/5 x. Okay, and so that'll be helpful to form one of our limits of integration. And then the next thing we need to do is solve for z, for the inner limits of integration for z here. So solve for z in the 15z equals 60 minus 12x minus 20y. So dividing everything through by 15, we're going to get z is equal to 4 minus 4/5 x minus 4/3 y. Okay, so this would form the lower and upper limits of integration for the innermost integral. This will form the second limit of integration for the middle integral for y, and then we'll integrate from 0 to 5 for the outer integral. Okay. All right, so the integral then that we're trying to calculate here, the integral. I'm just going to write that as a single integral over q of stuff is equal to, let's see what we have here, the integral from 0 to 5, that's the dx integral. Then the integral from 0 to 3 minus, let's see, 3/5 x. That's coming from here. That's the dy integral, and then the integral is going to go from 0 and then to z here. So that's going to be 4 minus 4/5 x minus 4/3 y. And that's going to be for z squared plus y squared times rho, which was 1 plus y plus, I think I forgot an x, I did, didn't I? Yeah, rho was 1 plus x plus y plus z, and then dz, dy, and then dx. Okay? All right, so to actually calculate this integral, it's anything with an x or a y is constant with respect to this. So we really have this integral and this integral. So we would multiply this out and then integrate each term by term and then replace all the z's with that. To do this integral, I'm actually going to plug it into maxima, and what it came out to be was 316 over 3. Okay, so I hope that was helpful. And then let's move on to part B, I believe. B, yeah. Okay, let's see if I can squeeze in B here. All right, so B has a very similar situation here. We're going to project the order here now is going to be what, dx, we need a little more room here. Shoot, see if I can squeeze it in. Okay, so the order here is going to be dy d z dx. So again, projecting onto the d z dx means we're going to project onto the zx plane or the xz plane. Okay, so the last two will tell us the way that we want to project. So if we look at the graph there, the projection is going to be. It looks very similar to the case, except for this would be z and this would be x. In our previous one, we had x and y. So just recognize those are different planes. So the shape of the graph is going to be very similar in this case as well. For the z-axis, this is 0, 4. And then for the x, this is at 5 and 0 again. Okay, and then, oh, sorry, no, this is at, yeah, 5 and 0. Yeah, that was right. Okay. Okay. And so if we solve this for z, we get z is equal to 4 minus 4/5 x. So that'll be the middle integral. And then again, we're going to solve for y. So y in 20y equals 60 minus 12x minus 15z. So y is going to equal, 3 minus 3/5 x minus 3/4 z. Okay. All right. And so the integral in this case is going to be the integral over q is going to equal, for the, let's see, the outer one is x, is going to be 0 to 5 again. And then for z, we're going to have here 0 to, what was it, 4 minus 4/5 x. And then the inner integral will be from 0 to y, which is 3 minus 3/5 x minus 3/4 z. And then again, the integrand will be the same. So z squared plus y squared, parentheses 1 plus x plus y plus z. This is the density function. And then what do we have here? We have dy dz dx. Okay. And likewise again, with this one, we're going to plug it into Maxima and calculate it. And when we do that, we got 316 over 3. Okay. And it shouldn't be surprising that these two results are the same. Again, we're covering the same region. We're covering the same volume, the same surface, the same, everything's the same. It's just the projection of how we're approaching it is different. So we should expect that the value comes up to be the same. So 2 out of 2 so far come out to be the same. I'm going to go ahead and erase this, and then we'll cover the last two. All right. Keep that information. Okay. All right. In part C, the order is, what is the order here? We got, excuse me, getting over a cold still. Integration is dx, dy, no, d with z in this case, dy. Okay, so in this case, we're going to look at the last two. So we're going to project onto the yz plane. Put that up here. Let's see, so y and z. Okay, so then this one, it looks a very similar form here, except for the y-intercept here is going to be at 3 and 0, and the z is going to be at 0 and 4. Okay, let's see, and then the equation of this line is going to be solving for z. Again, it's going to be z is equal to 4 minus 4/3 y. And let's see, we need to solve for x in this case. So we have 12x is equal to 60 minus 20y minus 15z. So that means that x is going to equal 5 minus 5/3 y minus 5/4 z. Okay. All right. So the integral over q is going to equal the integral So the outer one with respect to y here is going to go from 0 to 3. And then we're going to have the integral from 0 to, looks like 4 minus 4 thirds y. I'm going to have the integral from 0 to 5 minus 5 thirds y minus 5 fourths z. And then we're going to have z squared plus y squared rho. And then dx dz dy. And again, plugging this into maximum, we get the expected result of 316 over 3. Okay. Last but not least, here we go. The integration order in this case is going to be with respect to dx, dy, and dz. Okay, so if we look at the projection on the plane here, it's going to be exactly the same shape and form as the one that we just did up here. In fact, uh, you kind of think like we did this one last time. So maybe we'll just do that. Yeah. So we did this one last time. So now we're going to do DZ. So it's kind of like the uh, in the previous lessons where we had done the uh, changing the direction, right? We're doing the exact same thing here. So now we're going to go this way and we're going to look at DZ. Here we looked at DY. So it's exactly the same format, but we're taking our shift this way. So we're going to integrate up the value. And so we need to express these in terms of heights for Z, Y, and so on. Okay. So that means that Z equal to 4 minus 4 thirds Y. Inversing and solving for y is going to give me that y is equal to 3 minus 3/4 z. Okay, so that's again because we're going this way now. So that's the height of the function y with respect to z. Okay, so z is the independent variable there. Okay, so that's going to be the middle integral, and then z is going to go from 0 to 4 here. Okay, and then we just need to rearrange the middle part to solve for x, which is already done. So that one actually stayed the same. So actually, there's not a lot of extra work on this one. So q is going to equal the integral from, this is z now, so we're going to go from 0 to 4. And then the integral, this is for y, so it's going to go from 0 to 3 minus 3/4 z. And then the integral here is going to be from 0 to, just like in the previous example, 5 minus 5 thirds, y minus 5/4 z. Oh, excuse me. And that's going to be z squared plus x. No, not x. Is it y squared? And then rho, and then dx, dy, dz. Okay. Again, plugging this into maxima and calculate. We get 316 over 3 as our respective result. Okay. So the real trick on all of these is just being able to recognize, first of all, the projection into the corresponding plane. How do you know what projection to look at? The last two variables will tell you what projection to look at. And for a lot of the geometries and use of, I use GeoGebra to get a three-dimensional view of the shape or the function, and then using the projection there is really easy to see. And then just making sure you know which direction your rectangle is going is the key to solving the rest of those. Okay. All right. So I hope that was helpful, and I will see you in the next video.